There is a proof sitting in a physics journal from 1957, and 3/4 of it was cut out before anyone was allowed to read it. The man who wrote it had taken the equation that governs all of reality, the one we trust to 12 decimal places, and shown that the one step every textbook still teaches you, the moment where the wave function collapses and the world settles on a single outcome, was never needed. It was never in the equation. Someone added it by hand to cover up what the math actually says. So the only honest question left is what the math actually says, and the answer is the part that never made it into a press release. The other outcomes do not vanish. They keep happening, each in its own sealed world, including the world where you do not die. The man who proved this believed it about himself so completely that he told his family to throw his ashes out with the household trash. His own advisor buried the work. The field ignored it for 10 years. The reason you got the comfortable version, the one with the tidy little collapse, is that the honest version does something to the idea of you living one life and reaching one ending that almost no physicist has ever been willing to say into a microphone. Over the next couple of hours, we follow that buried proof out of a Princeton dormitory in 1954 into the hands of the advisor who carried it across the Atlantic to Niels Bohr to have its language quietly stripped out through the 1970 paper that finally gave it the name Many Worlds, into the laboratories that confirmed the mechanism that makes the branching physically real, and all the way to a suicide note written years later by the man's own daughter, asking to be thrown out with the garbage so that she could reach the correct parallel universe and find her father. So get comfortable and subscribe or join if you have not yet, because this channel runs on the people who stay for the long, strange ones. There is a Patreon as well, where these threads run wider, across physics and time and collapse, and the parts of the universe that were never built with you in mind. Stay to the end, because by the time we reach it, you will understand why the man who removed death from the equations would tell you, if you could ever reach the branch he is still in, that you are never going to experience your own. Let's go back to where this began. There is a filing cabinet in McLean, Virginia, and for a few years in the early 1980s, it held the ashes of a man who had decided, with the cold confidence of someone who had done the math, that he could not actually die. His name was Hugh Everett the Third. He had told his family more than once, and without the slightest sign of distress, that when his body finally quit, they were not to bury him, and they were not to scatter him somewhere green and dignified. They were to throw him in the trash, with the coffee grounds, with the junk mail, and after his widow kept the urn in that filing cabinet for a while, unable for a long time to actually do it, she eventually did what he asked. What was left of him went out with the household garbage on an ordinary collection day, and that was the end of the physical record of one of the strangest minds the 20th century produced. That is not a figure of speech. That is the literal disposal of the literal remains of the man who, at 26 years old, sat down and wrote what may be the only fully honest answer anyone has ever given to the single deepest unsolved problem in physics. And the reason he could shrug at his own funeral, the reason he could chain smoke and drink heavily and carry an extra 80 pounds and look at his own mortality with what people around him described as genuine indifference, is that he believed his own work had proven something that no sane person is supposed to be able to believe. He believed that from the inside, from the only point of view you will ever have, you never experience the moment of your own death. Not because of heaven, not because of the soul, because of an equation. Hold on to that. We are going to come back to the trash, and to the filing cabinet, and to why a brilliant man let himself believe the most dangerous idea a person can hold. But to understand how he got there, and why almost nobody has heard his name even though physicists today argue about his idea constantly, you have to understand what he actually did. Because what he did was solve a problem that you were handed a softened, sanitized, frankly dishonest version of, almost certainly by a teacher you trusted. And the real version has been sitting in a physics journal since 1957 with 3/4 of it cut out, removed, deleted by the one man on Earth who was supposed to protect it. So let us start with the problem, because the problem is older than Everett, and it is so quietly deranged that the entire structure of how quantum mechanics gets taught was built specifically to keep you from noticing it. Here is the thing about the equation at the center of all of this. Quantum mechanics has a master equation, written down by Erwin Schrodinger in 1926. And that equation is, in a very specific sense, perfect. It is smooth. It is continuous. It is completely deterministic. If you tell the Schrodinger equation the exact state of a system right now, it will tell you the exact state of that system at every moment in the future and every moment in the past, with no gaps and no dice and no surprises. In that respect, it is exactly like the equations Isaac Newton wrote down for falling apples and orbiting moons. Feed it the present, turn the mathematical crank, and the future rolls out in front of you like track in front of a train. There is nothing random in it, anywhere. And the predictions that come out of that equation are the most accurate predictions in the history of human thought. Quantum electrodynamics, which is built on this framework, predicts the magnetic behavior of the electron and matches the measured value to 12 decimal places. To give you a sense of what 12 decimal places of agreement actually means, imagine measuring the distance from New York to Los Angeles and being off by less than the width of a single human hair. That is the level of agreement we are talking about. This is not a tentative theory. This is the most ruthlessly tested idea we have ever had, and it has never once been caught in a mistake. But here is where the floor opens up. The thing the equation describes, the thing it evolves so smoothly and so deterministically, is called the wave function. And the wave function does not describe a particle sitting at a location, it describes something much stranger. It describes a particle being in many states at once. An electron in an atom is not at one spot with a definite energy. According to the equation, it is in a blend, a superposition, of many positions and many energies simultaneously, all of them carried along together inside the wave function, all of them evolving in lockstep. The equation does not just permit this, it demands it. A particle that goes through a barrier with two openings in it goes through both openings as a spread out wave of possibility, and the two halves of that wave come back together on the far side and interfere with each other, ripple against ripple. In a pattern you can photograph. You can do this experiment with single particles fired one at a time, so slowly that only one is ever in flight, and the pattern still builds up, which means each single particle went through both openings and interfered with itself. That is not a fringe claim. That is the most reproduced result in modern physics. The particle was in two places at once, and the math says so, and the photograph proves it. So the wave function spreads, it splits into possibilities, it carries every option forward at the same time. All of them equally real inside the equation, none of them favoured. That is what the Schrodinger equation does, every second to everything. And then you look. And you only ever see one. That is the problem. That is the entire problem, and once you see it clearly, you will never be able to unsee it. The equation says the particle is in a superposition of being here and being there. You put a detector down to find out which. And the detector reads here. Just here. One spot. One answer. The other possibility, the one the equation insisted was equally real a fraction of a second ago, is simply gone. Not improbable, not hiding, gone, as though it had never been in the math at all. And nothing in the Schrodinger equation tells you why. The equation describes the spreading. It says nothing whatsoever about the collapsing back down to 1. The smooth deterministic machine produces a fan of possibilities, and then reality, at the moment you check, somehow picks one and deletes the rest, and the equation that governs everything is utterly silent about how or when or why that happens. The man who first stated this cleanly was John von Neumann in 1932, in a book so mathematically rigorous that for decades it was treated as the final word. And von Neumann, who was almost certainly the most powerful pure mathematician alive at the time, did something that should disturb you more than it apparently disturbed him. He looked at this gap, this place where the deterministic equation fails to account for the single definite world you actually live in, and rather than solve it, he papered over it. He said, in effect, that nature runs on 2 completely different rules. He called them Process 2 and Process 1. Process 2 is the Schrodinger equation, the smooth deterministic spreading of the wave function, which operates whenever nobody is looking. And Process 1 is the collapse, the sudden discontinuous jump where the fan of possibilities snaps down to a single outcome, which operates whenever a measurement is made. Sit with how strange that is. The most important physical theory ever devised does not have one law. It has 2 laws that contradict each other, and the theory itself contains no rule for when to switch from one to the other. It just says, when a measurement happens, stop using the real equation and use the other thing instead. The smooth one runs the universe right up until somebody checks on it, and then a different rule takes over for an instant, does something the main equation forbids, and hands control back. No mechanism, no trigger you can point to, no equation for the moment of collapse itself, just an instruction to switch. I want to be very precise here, because this is the exact point where the teaching gets dishonest. Collapse is not a law of physics. There is no collapse equation. There is no measured collapse time, no collapse force, no collapse field. Collapse is a thing physicists add by hand after the fact to force the beautiful spreading equation to agree with the single boring world we observe. It is not a discovery. It is a correction fluid. It is the place where the theory admits it cannot explain the one thing every human being experiences, which is that the world has one outcome and not a smeared cloud of all of them. Collapse is not a law. It is an apology for not having one. And the apology has a name. The whole bundle of attitudes built up around treating collapse as just the way things are. The official position that you should shut up and calculate and not ask what is physically happening, that bundle is called the Copenhagen interpretation, after the city where Niels Bohr held court as the most authoritative figure in physics for a generation. Bohr was not a villain. He was a genuinely deep thinker who had wrestled with this harder than almost anyone. But the position he and his circle settled into, the position that became orthodoxy, that became the thing in your textbook, amounts to this. Do not ask what the wave function is. Do not ask what is really there before you measure. Do not ask what physically causes the collapse. The math gives you the right probabilities, so use the math, and treat any further question as a kind of philosophical bad manners. You were taught that this was settled. You were taught some version of the line where the wave function collapses when an observation is made, delivered in the tone of a finished fact, like the boiling point of water. What you are not told is that the collapse has never been observed as a physical process, has never been written into a single fundamental equation, and is regarded by a large and growing number of serious physicists as a confession dressed up as a principle. The cleanest statement of the situation is also the most uncomfortable one, For 100 years, the foundation of our most successful theory has been a step that the theory cannot justify and that we keep performing anyway because the alternative is too unsettling to look at directly. A 26-year-old graduate student at Princeton looked at it directly, and what he saw was so simple and so devastating that it took the people around him years to admit they could not refute it and the rest of their lives to avoid admitting what it meant. His insight was almost embarrassingly clean. He asked a single question that nobody in authority wanted asked out loud. What if there is no process 1? What if there is no collapse at all? What if the smooth deterministic equation, the one we trust to 12 decimal places, the one that has never been caught in an error, is simply telling the truth all the time, with no exceptions, even during a measurement, even when a person is looking? What if you just take the equation literally? And the reason nobody wanted that question asked is that the answer is monstrous. If the wave function never collapses, if the equation runs without interruption through the act of measurement, then the other possibilities do not vanish when you look. They cannot vanish, because nothing in the equation can make them vanish. So when you measure the particle that was in a superposition of here and there, and you see here, the version of events where it was there does not get deleted. It continues. It evolves forward, exactly as the equation says it must, carrying with it a version of the detector that read there, and a version of the laboratory where there was the answer, and a version of you who saw there and is right now in that branch, certain that there is the only thing that happened. Both outcomes are real. Both yous are real. The equation, taken honestly, does not describe one world settling out of a cloud of maybes. It describes a single unbroken structure in which every outcome that can happen does happen, each in its own branch, each branch containing its own copy of you, none of them more real than any other, all of them sealed off from one another forever. That is what the man whose ashes ended up in the trash wrote down in 1956, not as poetry, as a proof. He showed with the mathematics that if you assume the Schrodinger equation always applies and never gets interrupted, you automatically get an observer who sees a single definite result and who calculates exactly the probabilities the Copenhagen rules give, without ever needing to add collapse by hand. The collapse, he showed, is not something that happens out in the world. It is something that happens inside each branch to each copy of the observer as a feeling of definiteness. Every version of you sees one outcome and feels certain it was the only one, and every version is wrong about that in exactly the same way. He had not added anything to physics. That is the part that should genuinely unsettle you. He had not invented a new force, or a new particle, or some exotic mechanism. He had done the opposite. He had taken something away. He had removed the one piece of quantum mechanics that nobody could explain, the collapse, the apology, and shown that the theory works perfectly without it, and that the price of keeping the theory honest is accepting that reality is constantly, silently, unstoppably dividing into countless copies, and that you are dividing along with it. The math was clean, the logic was airtight. His own advisor, a man who would go on to coin the phrase black hole and to train an entire generation of American physicists, read it and could not find the error, because there was no error to find. And then that same advisor took the thesis apart. He cut roughly 3/4 of it out. He pressured the young man to soften the language, to bury the most radical claims, to reframe a frontal assault on the reigning orthodoxy as a polite footnote to it. The version that finally reached print in 1957 was a fraction of what had been written, stripped of its sharpest arguments, retitled into something deliberately bland. And the young man who wrote it understood exactly what had been done to his work, and he did something that, given how right he turned out to be, is one of the quiet tragedies of modern science. He left. He walked out of physics entirely at 27 with the answer to the measurement problem in his hands, and he never published another word of theoretical physics again. He took a job at the Pentagon. And the man who had just proven that every possible outcome is equally real spent the rest of his career calculating, in cold operational detail, how many millions of human beings would die in each possible outcome of a nuclear war. To understand how the most important idea in the foundations of physics got buried by the person who understood it best, and why that person then chose to spend his genius on the machinery of mass death, you have to go back to a graduate dormitory at Princeton, and to a night that began, by Everett's own account, with a slosh or two of sherry. Hugh Everett the Third was born on the 11th of November 1930 in Washington, D.C., into a family where the men were named in sequence, which is a small detail that matters more than it should, because it tells you he grew up inside a structure of inheritance and repetition, a line of identical names stretching backward and forward, the same person recurring across generations. He was, from the start, the kind of brilliant that makes adults uneasy. As an undergraduate at Catholic University, a devout institution, a teenage Everett constructed what he considered a rigorous logical proof that God does not exist, and mailed a version of it to Albert Einstein. Einstein, remarkably, wrote back. It was a polite note, the sort of thing a famous man sends to a precocious boy. But Everett kept it, and the episode tells you something about him that never changed. He did not believe a thing because it was comforting, or because the right people believed it. He believed a thing because the logic forced him to, and he followed the logic wherever it went, even when it went somewhere no one wanted to follow. He arrived at Princeton in 1953 to do graduate work, originally in mathematics, and then in physics, which at Princeton in those years was the center of the universe. Einstein was still alive and walking the grounds of the Institute for Advanced Study. John von Neumann was nearby. The department was thick with the people who had built the bomb, and the people who had built the theory the bomb relied on. Everett took a course in mathematical physics from Eugene Wigner, a future Nobel laureate, and he passed his general examinations in the spring of 1955, and somewhere in there he came under the supervision of a 30-something professor named John Archibald Wheeler, who is the second person you need to understand. Because everything that happened to Everett happened through Wheeler, and Wheeler was a man with a divided heart. To understand Wheeler, you have to understand who his hero was. In 1934, as a young researcher, Wheeler had gone to Copenhagen to study under Niels Bohr, and the experience marked him for life. He revered Bohr. Not respected, revered, he would later describe his own entire philosophy of physics, which he called radical conservatism, as something he had learnt at Bohr's side, the idea that you push the established principles to their absolute breaking point, but you do not abandon them. In 1939, Wheeler and Bohr had co-authored the foundational paper on nuclear fission, the theoretical work that explained how a uranium nucleus splits, work that fed directly into the Manhattan Project. Bohr was not an abstraction to Wheeler. Bohr was the man who had shaped him, the father figure of his intellectual life, and the Copenhagen interpretation was not just a position Wheeler held, it was Bohr's position. To attack it was, for Wheeler, something close to attacking the man he loved most in physics. And now this graduate student in his charge had written something that did not just question the Copenhagen interpretation, it dismantled it. It showed that the central move, the collapse, was unnecessary, and it did so without a single error Wheeler could point to. You can feel the bind Wheeler was in. He was honest enough to see that Everett was right, or at least that he could not prove Everett wrong, and loyal enough to Bohr that he could not bear to let the work go out into the world as the weapon it actually was. The idea itself had not arrived in a careful, methodical way. It had arrived, as the best ideas often do, sideways, late at night. Fueled by alcohol and the freedom of not yet being important enough for anyone to police your thoughts. By Everett's own much later recollection, the seed was planted one evening in 1954 in a Princeton dormitory after what he described as a slosh or two of sherry in a bull session with a fellow graduate student named Charles Misner and a visitor named Age Peterson. And the detail that makes this almost too perfect is who Age Peterson was. Peterson was Niels Bohr's personal assistant. He was, in that room, the living embodiment of the Copenhagen orthodoxy, the man whose job was to help Bohr think. And it was in conversation with Bohr's own assistant, tossing around what Everett called ridiculous things about the implications of quantum mechanics, that Everett first started pulling at the thread that would unravel Bohr's life work. The orthodoxy was in the room when its undoing was conceived, and it did not see what was happening, because at that point it was just sherry and talk. But the talk turned into something. Over the following year and a half, Everett worked the casual provocation into a full mathematical theory, and in January of 1956, he handed Wheeler a long, dense, completed draft. The title he gave it was deliberately grand. Quantum Mechanics by the Method of the Universal Wave Function. And that phrase, universal wave function, is the whole revolution compressed into 4 words, so let me make sure the weight of it lands. The wave function, remember, is the thing the Schrodinger equation evolves. In ordinary practice, physicists write a wave function for a small thing. An electron, an atom, a photon, the system under study. And then they treat everything else, the laboratory, the measuring device, the physicist, as standing outside the wave function, as classical, as the solid definite world that does the measuring. That division, the small quantum system on one side and the big classical observer on the other, is baked into the Copenhagen way of doing things. It is the line on one side of which the equation applies, and on the other side of which collapse takes over. Everett erased the line. He said there is no outside. If quantum mechanics is true, and it is the most accurate theory we have, then it must apply to everything, with no exceptions, because a law of nature that only applies to small things and politely switches off for big things is not a law of nature, it is a convenience. So he wrote a single wave function for the entire universe. One wave function. Everything in it. The electron and the detector and the laboratory and the physicist and the coffee cup on the desk and the distant stars, all of it. One enormous wave function evolving smoothly under the one equation forever, with nothing standing outside it to collapse it. Because there is no outside. Because it is the universe. And once you do that, once you put the observer inside the wave function instead of outside it, the collapse problem does not get solved so much as it dissolves. There is no longer anyone standing outside to perform a measurement on the system from a privileged classical vantage point. There is only the system measuring parts of itself with everything obeying the same single equation. And when one part of that universal wave function, the part that is a measuring device, interacts with another part, the part that is a particle in superposition, the equation does the only thing it can do. It correlates them. It entangles them. The device that was in a definite state becomes a superposition too, one branch of it reading here and another branch reading there. And the physicist who looks at the device becomes a superposition of a physicist who saw here and a physicist who saw there, and the two never interact again, and each one is, from the inside, completely convinced that a definite single thing happened. Everett needed a way to describe how each branch sees its own definite reality, while the whole thing remains a single undivided superposition. And the tool he built for that is called the relative state. The state of the particle is not absolute. it is relative to the state of the observer. Relative to the branch of you that saw here, the particle is definitely here. Relative to the branch of you that saw there, it is definitely there. Both statements are true at once, because both branches are real at once. And there is no fact of the matter about which one is the real you, because the question itself is malformed. There is no single you. There are two, and a moment ago there was one, and the one became two the instant the measurement entangled you with the outcome. In an early draft, Everett reached for an image to make this intuitive, and the image he chose was an amoeba. Picture a single amoeba that splits into two. Each daughter amoeba has all the memories of the original, because each one inherited the same internal structure. Neither daughter is the original, and neither is a copy. They are both equally the continuation of the thing that split. Now imagine that the amoeba had a mind, and that each time it divided, each daughter remembered being one amoeba, and had no awareness whatsoever of having divided, no sense that there was now another version of itself swimming away in the other direction. That, Everett said, is you. Every time the universal wave function branches, and it branches constantly, at every quantum event everywhere, you divide like the amoeba, and each version of you remembers a single continuous past and feels like the one and only you, and has no access to the others, and no way to even know they exist. The splitting leaves no trace you can detect from inside. That is why it feels like collapse. Collapse is what branching feels like from the inside of a branch. To feel why Everett's move was not just clever, but necessary, you have to see the trap that the collapse picture walks into, the trap von Neumann himself had laid out and then declined to escape. It is sometimes called the von Neumann chain, and it is the part of the measurement problem that has actual teeth. Go back to the particle in superposition, here and there at once. You bring a detector to measure it, but the detector is made of atoms, and atoms obey the Schrodinger equation, so when the detector interacts with the superposed particle, the equation does not let the detector pick a side. It correlates the two. The pointer that should read here now reads here and there at once, a superposition of a detector that fired and a detector that did not. The superposition has not collapsed, it has spread from the particle into the machine. Fine, you say, then the collapse happens when a person reads the pointer. But the light bouncing off the pointer into your eye is also made of physics, so now the light is in a superposition of carrying the here image and the there image. And your retina is physics, so your retina goes into superposition. And your optic nerve, and the neurons in your visual cortex, and whatever it is in your brain that constitutes the experience of seeing a number. The superposition climbs the chain, link by link, particle to detector to photon to eyeball to neuron, and at no point, nowhere, does the Schrodinger equation contain an instruction that says, "Stop here." This is where the cloud of maybes becomes a single fact. Von Neumann proves something genuinely disturbing about this chain. He showed that you can place the cut, the boundary where you stop using the smooth equation and impose the collapse by hand, at any link you like, and you get exactly the same experimental predictions. Put the cut at the detector, or at the retina, or at the cortex, and the numbers come out identical, which sounds reassuring until you understand what it actually means. It means the theory is telling you that the location where reality becomes definite is physically undetectable, that there is no experiment that can find the seam, because there is no seam, because the collapse is not a real event in the world that leaves a mark you could go looking for. The cut is a thing physicists draw on the diagram. Nature does not draw it anywhere. Eugene Wigner, the same Wigner who had taught Everett at Princeton, pushed this to the breaking point with a thought experiment that has come to be called Wigner's friend. Put your friend in a sealed laboratory with a superposed particle and a detector. Your friend makes the measurement. From your friend's point of view, inside the lab, there is a definite outcome, here or there, a single fact. But you are standing outside the sealed lab, and from your point of view, the equation says the entire contents of that lab, your friend included, are now in a superposition, a blend of a friend who saw here and a friend who saw there, and that superposition persists until you open the door. So which is it? Was there a definite fact the moment your friend looked, or only when you opened the door and looked at your friend? The two of you cannot both be right under the collapse picture, because the collapse can only happen once. And Wigner, staring at this, reached for the only escape the collapse framework leaves open. He suggested, for a while, that maybe consciousness is what collapses the wave function, that the friend's mind, being something more than ordinary matter, is what tips the superposition into a single fact. It was an act of desperation dressed as a hypothesis. It located the seam in the one place no physics could examine, the inside of a mind, precisely because there was nowhere physical left to put it. This is not an old debate that died quietly. In 2019, a team led by Massimiliano Proietti at Heriot-Watt University in Edinburgh built an actual laboratory version of the Wigner's friend scenario, using photons as the observers and entanglement to play the roles of friend and outside observer, and they ran it. And what they found, within the assumptions of the experiment, is that the two observers can end up with records that cannot be reconciled into a single shared account of what happened. There was no one fact of the matter that both observers agreed on. The experiment put real pressure in a real laboratory on the comfortable idea that a measurement produces a single observer independent fact about the world. The thing Wigner had treated as a paradox to be reasoned about was now a result printed in a journal, and Everett's framework walks straight through all of it without breaking a sweat, because it refuses to draw the cut at all. There is no link in the chain where collapse happens, because there is no collapse. The superposition climbs from the particle to the detector to the photon to the retina to the neuron, and it does not stop, ever, and the friend in the sealed lab is genuinely in a superposition of having seen both outcomes, and so are you when you open the door, and so is everyone, all the way up, with no privileged place where the maybes turn into a fact. The friend branched. You branched. The mind is not where reality becomes definite. Reality never becomes definite. It only ever feels that way from inside a branch to a copy of you who cannot see the others. The consciousness that Wigner thought might be doing the collapsing is just one more thing the equation sweeps up into the superposition along with everything else. I want to stop here and correct something you were almost certainly taught wrong, because it is the perfect example of how the sanitized version works. You have heard of Schrodinger's cat, the cat in the box, alive and dead at the same time until you open the box and find out. You were probably taught it as a charming illustration of how weird and wonderful quantum mechanics is, a little paradox to make you smile. That is the opposite of what it was meant to be. Erwin Schrodinger devised that cat in 1935 as an act of sarcasm. He was disgusted by the idea that a quantum system stays in a superposition until observed, and he constructed the cat specifically to show how absurd that idea becomes when you scale it up to something you can see. He was not celebrating the paradox. He was using the cat to argue that the standard interpretation must be broken, because obviously, he thought, no real cat is ever both alive and dead, so something in the theory has to give. The cat was a weapon aimed at Copenhagen. And here is the part that should make you sit up. Everett's theory is the one interpretation in which Schrödinger's sarcastic cat is simply, literally true, with no absurdity to it at all. The cat is alive in one branch and dead in another, both real. And when you open the box, you split into a version who finds a living cat and a version who finds a dead one. The thought experiment built to destroy the standard view is the thought experiment Everett's view swallows whole. Schrodinger built a cage to trap the orthodoxy, and Everett walked in and lived in it. Now back to the long thesis, because the physical object itself matters. The draft Everett handed Wheeler ran to something on the order of 137 pages, depending on how you count the drafts that fed into it, which by the standards of a physics dissertation is enormous. Most of the great papers in physics are short. Einstein's paper on special relativity is about 30 pages. Watson and Crick announced the structure of dinar in roughly a page. Everett's manuscript was a sprawling, ambitious, almost philosophical treatise, and it contained things that had nothing to do with quantum mechanics narrowly understood. It contained an independent derivation of information theory. It worked out a mathematical theory of how correlation and information behave, partly because he needed those tools to make his argument, and partly because he was the kind of mind that, having started, could not stop building. It surveyed the existing attempts to make sense of quantum measurement and dismantled them one by one. And only then did it lay out pure wave mechanics, the universal wave function, the relative state, the branching, the amoeba, the whole architecture of a reality that divides without end. It was, by any honest assessment, a work of startling originality from a man who was not yet allowed to call himself a doctor, and the people Everett wanted to read it were not his fellow students. He wanted Bohr to read it. He wanted the orthodoxy to confront what he had done. So in the spring of 1956, the draft, by then circulating under a sharper and more provocative title, Wave Mechanics Without Probability, was sent out to several of the most prominent physicists alive, including Niels Bohr himself in Copenhagen. You can imagine, maybe, what a 25-year-old believes will happen when he sends a proof that dissolves a great man's life work to the great man himself. He believes the logic will speak. He believes that because the argument is correct, and because these are serious people who care about truth, the correctness will win. He believes that the velvet rope will part, and he will be welcomed to the other side, recognized, told yes, you saw it, you are one of us now. That is not what happened. What happened instead is that John Wheeler, caught between the student he could not refute and the mentor he could not betray, decided that the work could not be allowed to go out into the world in the shape Everett had given it. And so Wheeler did what powerful advisors do. He picked up the manuscript and he carried it across the Atlantic to Copenhagen to argue about it in person with Bohr and to figure out how to make it acceptable. He went, in his own words, to have it out. And what he brought back was not a vindication. It was a set of instructions for how to cut his student's masterpiece down to something the orthodoxy could tolerate. Wheeler was in Copenhagen in the spring of 1956, and he sat down with Bohr and with Age Peterson, the same Peterson who had been in the dormitory when the idea was born, and they went at it. Wheeler later described having 3 long and strong discussions about Everett's work. Think about that phrasing for a moment. Long and strong. These were not seminars. These were arguments. The kind of arguments that happen when people who hold power over a field encounter something that threatens the ground they stand on. And the thing they kept circling back to was not the mathematics. They could not touch the mathematics. The formalism was unbreakable, and everyone in the room knew it. What they fought about was the words. You can see this with unusual clarity because the correspondence survives, sitting in the archives. On the 22nd of May 1956, Wheeler wrote to Everett to report on the Copenhagen battle, and the sentence that captures the entire tragedy is this one. Your beautiful wave function formalism, Wheeler wrote, of course remains unshaken. But all of us feel that the real issue is the words that are to be attached to the quantities of the formalism. Read that again, slowly, because it is one of the most revealing sentences in the history of physics. The math is fine. The math is beautiful. The math is unshaken. The problem is the words. The problem is what the equations are allowed to mean. The orthodoxy could not attack what Everett had proven, so it attacked what he was permitted to say about it. This is the mechanism. This is how an uncomfortable truth gets managed by an institution, and it is worth being forensically precise about it, because the popular story of suppressed science always reaches for the language of conspiracy, of secret meetings and deliberate burials, and that is almost never how it actually works. There was no conspiracy. Nobody sat in a room and decided to destroy Hugh Everett. What happened was quieter and more human, and in a way, much worse. A revered old man could not absorb an idea that unmade his life work. A loyal former student could not bring himself to wound the old man. And a young nobody with no power and a degree he still needed had a thesis that stood between him and the rest of his life. The path of least resistance ran directly through Everett's manuscript, and so the manuscript is what gave way. Wheeler began pressing for changes. He wanted the language softened. He was particularly troubled by the splitting, by the branching, by the amoeba. The image of a person physically dividing into copies struck him as the kind of claim that would get the whole thing laughed out of the room, and he wrote marginal notes pushing back on it, wanting better words. Wanting the radical content wrapped in conservative packaging. He wanted, in a phrase he used, to make the thesis javelin-proof. He wanted it armoured against attack, and the way you armour a dangerous idea is you take the edges off it until there is nothing left to cut anyone. And in his eagerness to make peace, Wheeler did something that, if you care about intellectual honesty, is hard to forgive. He wrote to one of the hostile physicists, a man named Alexander Stern, who had dismissed Everett's work as theology, and Wheeler reassured him that Everett's thesis was not meant to question the present approach to the measurement problem at all, but to accept it and generalize it. That is a lie. A polite, well-intentioned, peacemaking lie, but a lie. Everett's thesis was not an acceptance of the Copenhagen approach. It was a refutation of it. The entire point was that collapse is unnecessary, that the emperor of quantum measurement had no clothes, and here was the student's own advisor writing to the establishment to assure them that no, the boy means you no harm, he agrees with you really, he is just adding a footnote. Wheeler was translating a declaration of war into a letter of submission, and he was doing it on Everett's behalf, without Everett's heart being in it. The cuts came next, and they were not minor. The long thesis, the 137-page treatise, was reduced to roughly 36 pages. 3/4 of it gone, and it matters enormously what got cut, because the cuts were not random trimming for length. The survey of competing interpretations, the part where Everett systematically showed why every existing attempt to solve the measurement problem failed, was removed. That was the part that made the case for why his solution was needed. The independent derivation of information theory, the deep mathematical scaffolding, was stripped out. The frank discussion of how Copenhagen was, in Everett's private words, a philosophic monstrosity, was gone. And the most provocative framing, the splitting, the branching language that made vivid exactly how strange the conclusion was muted and hedged until a casual reader could almost miss what was being claimed. What was left was retitled into the blandest phrase imaginable. Relative state formulation of quantum mechanics. Not wave mechanics without probability, which announced a revolution. Not anything with the word universal in it. Relative state formulation. A title engineered to slide into a journal without anyone noticing that the building was on fire. It was published in the journal Reviews of Modern Physics in the 1957 volume, a short paper of about 9 pages, and it was accompanied by something almost unheard of. Wheeler wrote his own companion paper, published right alongside it, a sort of chaperone, in which the senior man explained to the community how they should and should not read what the junior man had written. Wheeler's assessment praised the formalism while gently steering everyone away from the interpretation, insisting it be read as compatible with Bohr rather than as a replacement for him. Even in print, even at the moment of publication, the idea was being supervised. Everett defended the short thesis and received his doctorate. The oral examination took place on the 23rd of April, 1957, in front of a committee that included Wheeler and the mathematical physicist Valentine Bargmann and the experimentalist Robert Dicke. He passed. He was Dr. Everett now. He had the degree, and the thing he had actually discovered was sitting in a journal in a form that hid most of its power, wearing a title chosen to make it forgettable, with a note from his advisor attached explaining that it was less than it was. There is one more piece of this that you need, because it complicates the easy story and makes the real one stranger. The person who reviewed Everett's paper for the journal, the referee, was a physicist named Bryce DeWitt, and DeWitt did not like it. In a letter to Wheeler on the 7th of May, 1957, DeWitt laid out his objection, and his objection is one of the most quoted lines in this entire history. The scheme, he admitted, is beautifully consistent. He could not fault the logic. But then, he said the thing that almost everyone says when they first really grasp Everett. The whole state vector, DeWitt wrote, is simply too rich in content, by vast orders of magnitude, to serve as a representation of the physical world. It contains all possible branches in it at the same time. And he added a personal note that cuts to the human core of why people resist this idea. He simply did not feel himself splitting into copies. He did not experience the branching. So how could it be real? Everett's reply to that objection is the cleanest thing he ever wrote, and it is the reason you should not dismiss any of this. He pointed out that DeWitt's argument was exactly the argument that had been made against Copernicus. When Copernicus said the Earth moves around the Sun, people objected that they did not feel the Earth moving. The obvious, intuitive bodily experience said the Earth was still. And the answer that took a century to accept, is that of course you do not feel it. The physics explains precisely why you would not feel it. You are moving with the Earth, so there is no relative motion to sense. In the same way Everett said, of course you do not feel yourself splitting. The theory explains precisely why you would not. Each branch contains a complete copy of you, with continuous memories and no access to the others. The absence of the sensation of splitting is not evidence against splitting. It is exactly what the theory predicts you would experience. The thing you would feel, if branching were real, is precisely the thing DeWitt was describing as a reason to doubt it. You would feel like nothing was happening. You would feel like one person living one life. You feel that way right now. And here is the detail that should make the hair on your arms stand up, the one I have been holding since the start. Bryce DeWitt, the referee who objected, the man who said the theory was too rich to be real, the man who could not feel himself splitting, became, a little over a decade later, the single most important champion Everett's idea ever had. He is the reason you have ever heard the phrase that everyone now uses for this. Because the name many worlds was not Everett's. Everett never used it. He called it the relative state formulation, the theory of the universal wave function, pure wave mechanics. The phrase many worlds was coined by Bryce DeWitt, the convert, the man who had resisted hardest, and then, having failed to escape the logic, gave the thing its name and spent years dragging it out of the drawer where it had been buried. The man who tried to keep the door shut ended up holding it open. We will get to how that happened, because the timing of it, more than a decade too late and after the cost to Everett was already paid, is its own quiet indictment. But in 1957, none of that future help had arrived. In 1957, there was only silence. The paper came out, gutted and disguised, and the world of physics did its worst possible thing to it. It ignored it. There was no firestorm of debate. There was no wave of follow-up papers. The historian Max Jammer would later describe the theory as having been, for its first decade, one of the best-kept secrets of the century. It just sat there, unread or read and shrugged at, a curiosity from a student who had since left the field. The orthodoxy had not needed to destroy Everett's idea. It had simply declined to look at it, and declining to look is, for an idea, a kind of death. I want to name the pattern plainly, because it repeats throughout this story and throughout the history of physics, and once you see it, you will see it everywhere. The pattern is this. First, the idea is impossible. Then, when it turns out to be perfectly consistent, it is unimportant. Then, decades later, when it finally cannot be avoided, it becomes something everyone always sort of knew. The one thing the idea is never allowed to be, in the moment it actually matters, is correct and consequential at the same time. Everett's work was not refuted, it was filed. And the difference between being refuted and being filed is that a refutation at least takes you seriously. Filing is the thing you do to a paper you have decided not to think about. They did not beat him, they closed the drawer. And there is a final layer to 1957 that the people closing the drawer did not understand, a consequence buried in the mathematics that Everett had already worked out and had, by some accounts, already begun to apply to himself in private. If the wave function never collapses, if every outcome that can happen does happen in its own branch, then the principle does not politely stop at coin flips and particle detectors. It applies to every event, including the events that end a life. It applies to the branch where the car misses you and the branch where it does not. To the branch where the cells turn cancerous and the branch where they do not. To every fork where you might continue or might stop. And in every one of those forks, the equation does the same thing it always does. It keeps all the branches, including, always, at least one branch in which you are still here. Everett had not just removed collapse from physics. He had, without quite saying it out loud in the gutted published paper, removed something else, something far more personal, and he knew it, and he would spend the rest of his life living as a man who believed he had found the mathematical reason that he, personally, was never going to experience the end. The world had filed his proof. Everett understood what filing meant. It meant the conversation was over before it had started, that no amount of being right was going to open the door, that the velvet rope was not going to part for him no matter how clean the logic was. And so he made a decision that looks, on the surface, like surrender, and underneath is something colder and stranger than surrender. He stopped waiting to be understood. He turned his back on the entire field, and he walked into a building where being right actually counted for something, where the questions had definite answers and the answers had consequences measured in human lives. He went to work for the people whose job was to plan the end of the world. He had taken the job even before he defended. In June of 1956, with the thesis still in its long form and the fight over the cuts still ahead of him, Everett joined the Weapons Systems Evaluation Group, the WUSEG, a Pentagon outfit that did exactly what its name says. It evaluated weapon systems, specifically nuclear weapon systems and the wars they would be used in. The official reason for the move was practical. He was losing his draft deferment, and a defense job solved that. But the deeper reason is the one that should stay with you. Everett had a particular kind of mind, a mind that wanted problems with answers, and theoretical physics had just shown him that even when you produce the correct answer to the deepest question in the field can simply decline to care. The Pentagon did not decline to care. At the Pentagon, if your calculation was right, missiles got built or not built on the strength of it, and millions of hypothetical people lived or died inside your equations, and nobody filed your work in a drawer because nobody could afford to. In October of 1956, just a few months in, Everett attended a nuclear weapons orientation at Sandia, in Albuquerque, the kind of briefing where bright young analysts are shown what these devices actually do. By 1957, the year his quantum paper appeared and vanished, he had been made the director of the USEG Department of Physical and Mathematical Sciences. He was not a junior figure in this world. He rose fast, because he was very good at it. And what he was very good at was applying cold mathematics to the problem of mass death. I am not going to soften this, because the irony is the entire point, and softening it would be a kind of lie. The man who had just proven, in a thesis the world refused to read, that every possible outcome is equally real, that nothing is ever truly eliminated, that all the branches persist, now spent his days calculating which outcomes of a nuclear exchange were preferable. He worked on targeting. He worked on the optimization of where the warheads should go, and how many you needed to be sure. In 1959 he co-authored, with a colleague named George Pugh, a paper in the journal Operations Research titled The Distribution and Effects of Fallout in Large Nuclear Weapon Campaigns. It is a real paper, in a real peer-reviewed journal, Volume 7, and it is exactly what it sounds like. It is a mathematical study of how the radioactive fallout from a large-scale nuclear war would spread across populations, and how to think about it operationally. He contributed to a document known as SEG Report 50, completed in 1960, parts of which remain classified to this day, and which became one of the foundational analyses underpinning the doctrine that came to be called mutually assured destruction. By some accounts, he wrote software used in the first single integrated operational plan, the PSYOP, which was the actual master plan for how the United States would conduct a full nuclear war, the choreography of the end of civilization, reduced to a computer program. Think about the shape of this life. In the morning, he is the author of a theory in which there is a branch of the universe for every possible outcome, including every possible death and every possible survival, all of them real. None of them erased. In the afternoon, he is computing how to maximize the deaths in the enemy's branch and minimize them in his own. The physics says all the dead are still alive somewhere. The job says make sure that, in this branch, the right ones are dead. I do not think Everett experienced this as a contradiction, and that is somehow the most unsettling thing about him. If you genuinely believe that every outcome happens, that there is no fact of the matter about which world is the real one, then the moral weight of any single outcome gets strange and light. Why agonize over the branch where millions die, when there is an equally real branch where they do not, and you have no more claim to one than the other? I am not saying that is sound moral reasoning. I am saying it is where his own theory points, and that he is the one person who took the theory completely seriously, and that he then spent his life inside the one institution where that particular flavour of detachment was an asset rather than a horror. In 1956, he had married a woman named Nancy Gore. They would have 2 children, a daughter, Elizabeth, and a son, Mark. And the descriptions of Everett as a father are uniformly bleak in a quiet way. He was there and not there. His son Mark, who would grow up to become a musician of real talent, later described his father as a physical presence in the house, like the furniture. Not cruel, not violent, just absent in the way a man can be absent while sitting in the same room, lost inside calculations he never explained, drinking, smoking, gaining weight, present in body and gone everywhere else. The man who had written that there is a copy of you in every branch was, to the copies of his family in this one branch, barely reachable. The personal and the physical are not separate threads here. they are the same thread. A man who believed nothing was ever truly lost did not seem to know how to hold on to the people who were in fact right in front of him and slipping away. And yet he had not entirely stopped believing the door to physics might open. In 1959, 3 years after the gutting of his thesis, Wheeler arranged for Everett to travel to Copenhagen and meet Bohr directly. This was supposed to be the reckoning. The young man and the old master face to face at last, the proof carried not by an intermediary, but by the person who had created it. Everett went. He brought Nancy. He sat down with Niels Bohr, who was then 73 years old and near the end of his life, the most authoritative figure in the entire discipline, and Everett tried to make his case. It was a catastrophe. Bohr rejected the approach completely, not point by point, but as a whole, the way an immune system rejects a foreign body. There was no meeting of minds, no moment of recognition, no parting of the velvet rope. Everett later described the trip in flat, bitter terms. He said it was doomed from the beginning. He called it, in one recollection, a hell. The pilgrimage that was supposed to vindicate him confirmed instead that the door was not merely closed but welded shut, that the most important man in physics had looked directly at the answer to the field's deepest problem and felt nothing but the urge to push it away, and the contempt did not stay polite. Years later, one of Bohr's closest collaborators, a physicist named Leon Rosenfeld, who had been in the orbit of the Copenhagen establishment for decades, wrote down what that establishment actually thought of Everett, in private, where the manners came off. In a letter written in 1972, Rosenfeld described Everett's visit to Copenhagen and his attempt to, in Rosenfeld's words, sell the hopelessly wrong ideas he had been encouraged, most unwisely, by Wheeler to develop. And then, Rosenfeld wrote the sentence, Everett, he said, was indescribably stupid and could not understand the simplest things in quantum mechanics. Indescribably stupid. About the man who had produced the one interpretation of quantum mechanics that requires nothing but the equation everyone already agreed was correct. About the man whose idea a majority of working cosmologists would, within a few decades, take seriously enough to argue is simply true. The keeper of the orthodoxy looked at the most logically conservative idea anyone had ever proposed, an idea whose only crime was taking the existing math literally, and called its author too stupid to understand the basics. That is not the verdict of someone who had refuted Everett. It is the verdict of someone who could not, and who reached for the only weapon left, which is the assertion that the person who disagrees with you must simply be a fool. There is a grim little coda to Rosenfeld's contempt. A few years before that letter, in 1971, when the physicist John Bell had begun writing about Everett's ideas and giving them, in Rosenfeld's disgusted phrase, an air of respectability, Rosenfeld complained that Bell was lending dignity to what he called Everett's damned nonsense. Damned nonsense. The establishment had a vocabulary for this thing, and the vocabulary was the vocabulary of dismissal, of irritation, of a man swatting at something he wished would stop existing. At no point in any of it is there an actual argument. There is only the social fact of who was allowed to be taken seriously and who was not, and Everett was not, and the reason had nothing to do with whether he was right. I said earlier that there was a single bright moment in the Copenhagen disaster, and there was. And it is so on the nose that if it were fiction, you would roll your eyes. While Everett was in Copenhagen, sitting around at the Hotel Osterport, the trip already a failure, he and a colleague got to talking about an entirely different kind of problem, a problem in optimization, the mathematics of how to allocate limited resources to get the best result. And on a piece of hotel stationery, Everett worked out a general method for solving a whole class of these problems, a technique using what are called Lagrange multipliers, a method that later became known, to the small number of people who use it, as the Everett algorithm. Here is the irony, complete. The trip, meant to win him recognition for the deepest idea in physics, won him nothing. But on hotel notepaper, as a distraction from his own defeat, he sketched a piece of applied mathematics that would, a few years later, make him genuinely rich. Because that is the other thing about Everett that does not fit the tragic genius template. He was not a starving martyr. In August of 1964, he co-founded a defense contracting company called Lambda Corporation. Built substantially on exactly these optimization techniques, applied to military problems, and it made money. He later co-founded another company. He drove expensive cars. He had a comfortable house in Virginia. By the worldly measures America uses to keep score, Hugh Everett won. He was a wealthy, successful businessman who had cracked one of the deepest problems in the history of science as a side project in his 20s, and then walked away from the recognition, because the recognition never came, and the money was better, and the questions in the defense world actually got answered. But the questions that had driven him at 26 did not go away just because the field had stopped listening. He kept the manuscript. He kept thinking about it, and the thing he had proven about the branches, about the universe never eliminating an outcome, about there always being a version where you continue, settled into him not as an abstract result, but as a personal belief about his own existence, a belief he held quietly and acted on completely, with the lit cigarette and the next drink and the indifference to the body that was slowly failing him. He believed the math had set him free from the one thing every other human being fears. And while he sat in that classified building, erased from the field he should have led, drinking and computing the arithmetic of annihilation, the idea he had abandoned was beginning, very slowly and entirely without him, to come back to life. Because an idea that is filed instead of refuted has a dangerous property. It does not decay. It waits. It sits in the drawer being exactly as correct as the day it was written, and all it needs is one person willing to open the drawer and read what is actually there. And in 1970, the man who opened the drawer was the same man who had once tried hardest to keep it shut. Bryce DeWitt had spent 13 years not quite able to let it go. The objection he had raised as a referee, that the theory was too rich, that he did not feel himself splitting, had been answered by Everett with the Copernicus reply, and the answer had lodged in DeWitt and would not come loose. And in September of 1970, DeWitt did the thing that changed everything. He published an article in Physics Today, which is the magazine that lands on the desk of essentially every working physicist in America, with the title Quantum Mechanics and Reality. And in it, he laid out Everett's idea in plain, vivid, unmissable language, and he gave it the name that would make it famous and infamous at the same time: the many worlds interpretation. DeWitt did not soften it the way Wheeler had. He did the opposite. He described, in a passage that became notorious, what the theory actually claims if you take it seriously, that every quantum transition taking place on every star, in every galaxy, in every remote corner of the universe, is splitting our local world on Earth into myriads of copies of itself. Myriads of copies, not as metaphor, as the literal content of the equation. And DeWitt admitted with disarming honesty that when he first encountered the idea, the shock of it had been considerable, that there was something in it that did real violence to common sense. But he had checked the logic, the way you check a proof, and the logic held, and so he had decided that intellectual honesty required him to advocate for it rather than to keep flinching away from it. The article detonated, in the slow way that articles detonate in a scientific field. Suddenly people who had never heard of Everett were arguing about him. And 3 years later, in 1973, DeWitt and a graduate student named Neil Graham edited and published a book through Princeton University Press titled The Many Worlds Interpretation of Quantum Mechanics. And inside that book, finally, for the first time, in full 16 years after it was written and butchered, they printed Everett's long thesis. The whole thing, the 137 pages. The theory of the universal wave function restored, the version with the survey of failed interpretations, and the information theory and the splitting language all intact. The version Wheeler had carved away, the proof that had been filed in a drawer, was pulled back out and set in front of the world in the shape its author had originally given it, and this time the world was, slowly, ready to look. But before we follow the idea into the laboratories that would finally make it respectable, you have to know what happened to the men who buried it, because the return of Everett's theory was something they had to live with, and one of them lived with it for a very long time and in a way that should complicate any simple story you want to tell about villains. Niels Bohr never accepted it. He died in 1960, 5 years after the gutted paper appeared, having looked directly at the most economical reading of his own theory and pushed it away to the end. Leon Rosenfeld kept his contempt warm into the 1970s, as we have seen. Those men are easy. They dismiss something they did not understand, and they died without understanding it. And history has not been kind to them on this particular point. But John Wheeler is not easy, because Wheeler understood it perfectly, and that is exactly what makes his story the hardest one in this whole account. To understand Wheeler, you have to know about his brother Joe. Joseph Wheeler was John's younger brother, a historian, and during the Second World War, he went to fight in Europe while John worked on the bomb. And at some point in 1944, Joe sent his brother a postcard from the Italian front. It carried 2 words: hurry up. Joe knew, in the general way that family members of bomb physicists knew, that his brother was working on something that might end the war. And the message was a soldier's plea to the scientist. Hurry up, finish it, bring this to an end before more of us die over here. And then, in October of 1944, Joe Wheeler was killed in Italy. The bomb that might have ended the war in time to save him was not ready. It would not be ready for almost another year. John Wheeler carried that for the rest of his life. He believed, or could not stop fearing, that if the work had gone faster, if the bomb had come sooner, his brother might have lived. 2 words on a postcard, hurry up, and a death that a different timeline might have prevented. It is why Wheeler threw himself so hard into weapons work afterward, the hydrogen bomb, the whole apparatus of Cold War physics. He was a man haunted, at the deepest level, by a single question. Could the past have gone differently? Was the timeline that killed his brother the only one? Or had there been a fork, a branch, a version where the postcard arrived in time to matter? Now hold that question in your mind, hurry up. Could the past have been otherwise? And look at the experiment Wheeler is most famous for proposing. Decades later, in 1978. It is called the delayed choice experiment. Take the double slit, the one where a particle goes through both openings as a wave and interferes with itself, unless you check which slit it went through, in which case it behaves like a particle that went through only one. Ordinary intuition says the particle must decide, as it passes the slits, whether to behave as a wave or a particle. Wheeler's insight was that you can wait. You can leave the choice of how to measure it until after the particle has already passed through the slits, until it is almost at the detector. And when you do, the particle's behavior still matches your choice. Choose to look for interference, and you find that it went through both slits as a wave. Choose to look for which path, and you find that it went through one slit as a particle. Your choice, made after the particle has already done whatever it did, appears to reach back and fix what it did. Wheeler put it in language that should stop you cold. The past, he said, has no existence except as it is recorded in the present. The delayed choice experiment was confirmed in the laboratory, first in the 1980s and many times since, and it holds up. Sit with the shape of that life for a moment, because the personal and the physical here are not two separate threads. They are one thread running in both directions. A man receives a postcard from his brother saying, "Hurry up." His brother dies because, he fears, the work did not go fast enough. He spends the rest of his life unable to stop asking whether that past could have been different. And then that same man proposes and lives to see confirmed an experiment demonstrating that the past is not fixed and finished, but is in some real sense still open, still waiting to be determined by a choice made now. Wheeler, haunted by whether his brother's death could have been otherwise, became the man who showed that the past does not have a single settled existence. He spent his grief building the physics of an unfixed past. I do not think that is a coincidence. I think it is the deepest kind of connection there is between a person and the work they do, and Wheeler, who saw everything, almost certainly saw it in himself. So here is the agony of Wheeler and Everett. Wheeler had a student who proved that every branch is real, that the fork is never resolved into a single line, that the past and the present and the future all coexist in one unbroken structure where nothing is ever eliminated. That is, in a sense, the ultimate answer to the question that haunted Wheeler. In Everett's universe, there is a branch where the postcard came in time, where Joe lived, and it is exactly as real as this one. Everett handed Wheeler the very thing his grief was reaching for, a physics in which the timeline that killed his brother is not the only one, and Wheeler could not take it. He cut it to a quarter of its length and sent his student away from the field, because the price of accepting it was betraying the other man he loved, Bohr, and because the conservative in him could not bear the metaphysical cost of all those worlds, and he could not stop circling it for the rest of his life. This is the part that reads almost as self-punishment. In his 1957 companion paper, Wheeler had championed Everett, carefully, with supervision, but championed him. Then he began to retreat. In a lecture in 1977 he wrote that he and others had once subscribed to Everett's view, but that in retrospect it looked like the wrong track. Around the Einstein centennial in 1979, he said he had reluctantly had to give up his support for the idea because, in his words, it carries too great a load of metaphysical baggage. Too much baggage. The man who proposed that the past has no existence except as recorded in the present, the man who would coin the phrase black hole and spend his life chasing the most extravagant ideas in physics, decided that Everett's worlds were the one extravagance too far. He spent decades publicly distancing himself from the best idea his best student ever had, the idea he himself could not refute. And I want to name the pattern this fits, because Everett is not the only one, and the repetition is the indictment. Go back to 1927 to the Solvay Conference, where Louis de Broglie proposed a version of quantum mechanics in which particles really do have definite positions at all times, guided along by a wave, a picture with no collapse and no paradox, the pilot wave. He was talked out of it, worn down by objections, and he abandoned his own theory and spent years teaching the orthodox view he had tried to replace. Then in 1952, 2 years before Everett's Sherry Night, a physicist named David Bohm revived and completed de Broglie's pilot wave theory, showed it was fully consistent, showed it reproduced every prediction of standard quantum mechanics with definite particles and no collapse. And the establishment's response to Bohm was not refutation either. Robert Oppenheimer, the most powerful physicist in America, reportedly said of Bohm's work that if they could not disprove it, they would have to agree to ignore it. Agree to ignore it. And Bohm, who was also caught in the McCarthy-era political machinery, had his passport taken, was effectively driven out of the United States, and lived much of his life in exile, in Brazil and then in England. His physics dismissed as a curiosity for decades, so count them. De Broglie talked out of his own correct idea and silenced for years. Bohm, completing it, attacked, exiled, ignored by agreement. Everett, proving collapse unnecessary, cut to a quarter and filed in a drawer and driven from the field. John Bell, who in 1964 proved the theorem that would eventually reshape the entire field, working in obscurity on the side, unrecognised for years. There is a pattern here, and the pattern has nothing to do with the quality of the physics. Every one of these people produced work that was logically sound and that the establishment could not refute. And every one of them was removed from the conversation, not by being proven wrong, but by being declared, in one way or another, not worth listening to. The mechanism was never a conspiracy. It was something more ordinary and more durable. It was the social enforcement of which questions a serious person is allowed to ask. And the questions these men asked were the ones that threatened the comfort of the people in charge. There is a final piece of Wheeler, and it is the one that I cannot read without flinching. Near the end of his very long life, Wheeler was interviewed by the biographer who was assembling the true story of Everett, and Wheeler, then in his 90s, said something about his old student that lands like a confession from a man running out of time to make one. He said that Everett had been disappointed, perhaps bitter at the non-reaction to his theory. And then he said this: "How I wish that I had kept up the sessions with Everett." The questions that he brought up were important. How I wish that I had kept up the sessions with Everett, the man who cut the thesis, who carried it to Copenhagen to have its language defanged, who wrote to the orthodoxy promising that the boy meant no harm, who spent decades publicly calling the idea the wrong track and too much baggage, sat at the end of his life and wished, simply, that he had kept talking to the student he had failed. The questions were important. He had always known they were important. He had spent 50 years pretending they were not. Because a name and a book are not the same thing as a mechanism, and the deepest objection to Everett, the one DeWitt himself had raised, was still standing. If the universe is constantly splitting into branches that all stay real, why does the world look so stubbornly classical and singular? Why does the cat come out either alive or dead, and never as a visible blur of both? Why do the branches not slosh back together and interfere with each other the way the two halves of a single particle's wave do in the double slit? What keeps the branch where you read here cleanly separated from the branch where you read there? So cleanly that you have never once in your life caught a glimpse of the other one. The answer arrived from a direction nobody had been looking. And it is the single most important development in this entire story, because it took Everett's idea from a philosophical position you could take or leave and turned part of it into experimentally confirmed physics. The answer is called decoherence. The first clear version of it was worked out by a German physicist named H. Dieter Zeh, who published the foundational paper in 1970, the same year as DeWitt's article, entirely independently, and it was developed through the 1980s and beyond into a precise and testable theory, largely by the Polish-American physicist Wojciech Zurek and others. Here is what decoherence says, and I am going to be careful with it because this is the part that is not interpretation, this is the part that is measured. When a small quantum system in a superposition interacts with a large environment, and by large I mean anything with a lot of particles, a detector, the air in the room, a single dust grain, a stray photon, the superposition does not stay neatly contained in the small system, it leaks. The information about which branch is which spreads out into the environment, getting recorded in the positions of countless air molecules and photons and atoms, entangling itself with the whole messy world. And once that information has spread into the environment, the two branches can no longer interfere with each other, because to interfere they would have to come back together perfectly, and that would require reassembling not just the system, but every single particle in the environment that the information leaked into, which is, for all practical purposes, never going to happen. The branches do not merge back, they decohere. They become, for all time, sealed off from one another, each one evolving forward as its own effectively classical world, unable to reach across to the others, or even to know they are there. That is why the cat is never a visible blur. The cat is enormous, made of uncountable particles, soaked in interactions with its environment, and so the moment the radioactive trigger does or does not fire, the alive branch and the dead branch decohere almost instantly and completely, and each one carries on as a self-consistent world, and the version of you in each one sees a single definite cat. Decoherence is exactly the mechanism Everett needed, and did not have the language for in 1957. It is why branching is irreversible. It is why you feel like one person. And it has been confirmed in the laboratory, repeatedly, in exquisite detail, watching superpositions lose their coherence to the environment at precisely the rates the theory predicts. The branching, in this specific sense, is not speculation. The mechanism that makes the branches stop talking to each other is measured physics. And once decoherence was on the table, the entire status of Everett's idea shifted. It was no longer a strange metaphysical add-on. It was, arguably, the most economical reading of the math, because it required nothing extra. The collapse interpretations have to add a collapse, an extra physical process nobody has ever observed. Everett, plus decoherence, needs only the Schrodinger equation that everyone already accepts, running without interruption, plus the entirely mundane fact that systems interact with their environments. The thing that had been called too rich to be real turned out to be the thing that needed the fewest ingredients. The converts followed. A British physicist named David Deutsch, who had actually managed to have dinner with Everett in 1977, near the end of Everett's life, became the most aggressive advocate of all, and Deutsch did something that mattered enormously. He used the many worlds picture to help invent the theory of quantum computation, the field that today has billions of dollars and the world's largest companies pouring into it. Deutsch has said plainly that he thinks the parallel branches are where a quantum computer does its work, that when a quantum computer factors a number faster than any classical machine could, it is, in effect, distributing the computation across the branches. You do not have to agree with that framing to notice the significance of it. The idea that got its author called indescribably stupid is now sitting underneath one of the most heavily funded technologies on Earth. By the time you reach the present, the names lining up behind some version of Everett are not fringe figures. The physicist Max Tegmark at MIT, the physicist Sean Carroll, who wrote an entire book, Something Deeply Hidden, published in 2019, arguing that Many Worlds is simply the most honest reading of quantum mechanics, and that the resistance to it is psychological rather than scientific. And the polls, for whatever the polls are worth, tell a striking story. They are small and informal, taken at conferences among self-selected attendees, so do not treat them as a census of all physics. But at a workshop Tegmark polled in 1997, Many Worlds drew 8 votes against 13 for Copenhagen, with a large undecided middle, which Tegmark noted was a remarkable shift from the days when Copenhagen reigned without challenge. At a Foundations conference in 2011, with 33 participants, roughly 1 in 6 endorsed Many Worlds. And an earlier informal poll of leading cosmologists and quantum field theorists reportedly found a majority willing to say yes. They thought the Many Worlds idea was true, with names like Stephen Hawking and Murray Gell-Mann counted among the sympathizers. Hawking is said to have regarded the question of whether Many Worlds is true as almost trivial. The world's obviously there in the math, and to have found the debate about it tiresome rather than open. I want to be honest about something, because the people who push back on this are not idiots, and you should know where the genuine disagreement lives. There is still no consensus. Many physicists find the proliferation of worlds extravagant and unbelievable, and there are real hard technical objections, especially around the question of probability. If every outcome happens, what does it even mean to say one outcome is more probable than another? There is serious, ongoing, unresolved work on whether the Born rule, the rule that tells you the probabilities, can be properly recovered inside a no-collapse picture, and reasonable people disagree about whether it has been done. I am not telling you many worlds is proven. It is not. What I am telling you is the thing that is actually true and actually buried, which is that it is not fringe, it is not crankery, it is a live and respectable contender held by serious people. And the version of the story where it was rightly dismissed as nonsense is a fiction maintained by people who found the idea uncomfortable. And before we go further, let me dismantle two things you have probably absorbed, because the popular versions of this idea are almost as misleading as the popular version of collapse. First, many worlds does not mean that anything you can imagine happens in some world. It does not mean there is a world where you can flap your arms and fly, or a world where the laws of physics are different, or a world where your wishes come true. The only branches that exist are the ones the Schrodinger equation actually produces, the outcomes with non-zero amplitude under the real physics. The branching is constrained, lawful, and specific. It is not a wish-granting multiverse. It is the bare consequence of one equation never being interrupted. Second, you may have heard that quantum mechanics proves consciousness causes the collapse of the wave function, that the mind is special, that observation requires an observer with a soul. A few serious people, including von Neumann himself and later Eugene Wigner, did flirt with the idea that consciousness might be what triggers collapse, precisely because nothing in the physics tells you where else to put the boundary. But that idea has steadily lost ground, and Everett's framework removes the need for it entirely. In his picture, there is no collapse for consciousness to cause. A measuring device branches whether or not anyone conscious ever looks at it. The dust grain decoheres the photon in an empty room on a dead planet in a galaxy no eye has ever seen. You are not the observer the universe is responding to. You never were. The universe was never waiting for your mind. It branches on its own, constantly, everywhere. And it would branch in exactly the same way if every conscious being in it vanished tomorrow. Now hold those two corrections together and feel where they leave you, because this is the consensus flip, the move that closes the last exit. The interpretations of quantum mechanics disagree about almost everything. Copenhagen says do not ask. The pilot wave theory of Louis de Broglie and David Bohm says the particle has a definite position all along, guided by the wave, and that theory was itself exiled and ignored in a story that rhymes with Everett's exactly. The spontaneous collapse theories say the wave function really does collapse, but as a rare random physical event with its own equation. Many worlds says nothing collapses and everything branches. They cannot all be right, and they fight bitterly. But here is the thing they are all forced to agree on, the thing that is true in every single one of them, the thing nobody wants to be the one to say out loud. The bare Schrodinger equation, the equation we trust to 12 decimal places, does not contain a collapse. It never did. Every interpretation that gives you a single definite world has to add something to the equation by hand to get rid of the other branches. An extra process, an extra rule, an extra postulate, and not one of those additions has ever been independently measured, and not one of them can say precisely when or how it operates. The disagreement between the interpretations is really a disagreement about what to bolt onto the equation to make the extra worlds go away, and the worlds are there in the equation to begin with. That is why you have to bolt anything on at all. You do not add structure to create the branches, you add structure to delete them. The other worlds are not the speculative part. The other worlds are what the math says if you leave it alone. The speculative part, the part with no evidence behind it, is the machinery we invent to make them disappear. So when you do something as ordinary as check which way a coin landed, the equation that governs reality says that you have just become two people, decohered from each other forever, one who saw heads and one who saw tails. Each certain it was the only outcome. This is happening in your body right now. Every time a sodium ion does or does not cross a channel in one of your neurons, every time a photon does or does not trigger a receptor in your eye, every quantum event in the warm, wet machinery of you is a fork, and the equation keeps both tines. And the version of you reading this sentence is one twig on a tree that has been branching without pause since before you were born and will go on branching, the math says without pause, through everything that is ever going to happen to you, including the end of it. And that is where Everett's private belief stops being a personal eccentricity and becomes the thing the whole story has been walking toward since the filing cabinet. Because the vindication, when it finally came, did not just confirm an abstract claim about cats and photons. It confirmed, or at least made frighteningly respectable, the one specific consequence that Everett had taken into himself and built his life around, the consequence that had let him drink and smoke and shrug at the failing of his own body. The branching has no off switch. There is always a branch where you continue. And if that is true, then from the inside, the only place you ever are, you never reach the end. The vindication came too late for him to see it, but it came in time to confirm that the most dangerous thing he ever believed was not the rambling of a bitter man. It followed from the math, and his daughter believed it too. To understand what Everett believed, and what he passed on, you have to follow the branching all the way to its most personal and most disturbing conclusion. The one that has a name now, a name coined by other physicists decades after Everett died. The thought experiment is usually called quantum suicide, and the conclusion it points to is called quantum immortality, and I want to walk you through it slowly, because the popular versions get it wrong in both directions, either treating it as obvious nonsense or as a guarantee of life everlasting. And it is neither. It is something more precise and more unsettling than either of those. Start with a machine. The version Max Tegmark used when he laid this out around 1997 and 1998 goes like this. You build a gun and you wire its trigger to a quantum measurement, something genuinely in superposition. A particle whose spin is equally likely to be measured up or down. Every time you pull the trigger, the device measures the particle. If it comes up one way, the gun fires. If it comes up the other way, the gun makes a click and nothing happens. So each pull is a clean 50-50 quantum coin flip between you dying and you surviving, with the outcome decided by an honest quantum event, not a mechanical one. Now sit in front of the gun and pull the trigger. From the outside, from the point of view of someone watching you, the prediction is exactly what your intuition says. Pull it once, 50% chance you are dead. Pull it 10 times, and the odds that you are still breathing are about 1 in 1,000. Pull it 50 times, and an observer watching will, with overwhelming probability, be standing over a corpse. That is the third-person story, and it is grim and ordinary. But now tell the story from the inside, from your own point of view, the only point of view you will ever actually have. According to Everett, every pull branches the world. In one branch the gun fires and that version of you is instantly gone, with no experience, no awareness, nothing, because death is precisely the cessation of experience. In the other branch the gun clicks, and that version of you is still sitting there, still conscious, still able to notice that you are alive. And here is the knife edge of the argument. You can only ever find yourself in a branch where you are still conscious, because the branches where you died contain no version of you to do any finding. Your subjective thread of experience, the sequence of moments that feels like being you, cannot pass through the branches where it ends. It can only continue down the branches where it continues. So from the inside, no matter how many times you pull the trigger, you always find yourself among the survivors. You pull it 50 times and you are astonished to be alive, and you would be astonished every single time, in every branch where there is still a you to be astonished. Because the you that would not be astonished is not there to feel anything at all. Generalize that from the contrived gun to your actual life and you arrive at quantum immortality. You do not need a rigged gun, because the universe is already firing quantum coin flips at you constantly. Every illness, every accident, every failing of the body has, somewhere in the branching, an outcome where you survive, however improbable, and your subjective thread, by the same logic, can only ever continue down the surviving branches. From the inside, you never experience the branch where it ends, because in that branch there is no inside. You never attend your own death. You only ever find yourself having, against all odds, survived again. And again. And again, down an ever-thinning thread of more and more improbable survivals, while in branch after branch you have, from everyone else's point of view, already died. I need to be fair about the status of this, because it is the place where serious people get off the train, and they have reasons. Tegmark, who formalized the thought experiment, does not actually believe it grants real immortality, and he has been careful to say so. There are genuine objections. Death is usually not a clean quantum coin flip. Most ways of dying are gradual, the slow degradation of a brain starved of oxygen, and the argument is much murkier when there is no sharp branch point between fully alive and instantly gone, when instead there are branches of being a little more damaged, and a little more damaged still. There are deep unresolved questions about what it even means to identify your future self in a branch, about whether the probabilities should be counted the way the argument assumes. This is not a settled result. It is a thought experiment that lives at the edge of what the theory can clearly say. I am not telling you it is true. But I am telling you that Hugh Everett believed it. Not the careful hedged version, the whole thing. By the accounts of the people who knew him and the biographers who have gone through his papers, Everett held as a genuine personal conviction that his interpretation meant he could not die, that his own consciousness would simply continue down the surviving branch, always, that subjective death was an illusion that the method exposed. And he did not hold this belief idly. He lived it. The heavy drinking, the chain smoking, the indifference to the obese and failing body, the refusal to do any of the ordinary frightened things that mortal people do to stay alive a little longer, all of it reads differently once you understand what he thought he had proven. Why would you fear the cigarette or ration the next drink if you have convinced yourself, with a proof you are confident no one can refute, that there is no branch in which you experience your own end? He was not being reckless in the way of a man who does not care whether he lives. He was being consistent in the way of a man who does not believe death is a thing that can happen to him from the only vantage point he has. He was acting on his own theorem, with his own body, every day, and then, on the night of the 18th into the 19th of July, 1982, in his house in McLean, Virginia, the body that he had treated as theoretically indestructible did the thing bodies do. His heart stopped. He died in his bed, of a heart attack at the age of 51. By the cold actuarial standards he had spent his career calculating with, he died young, decades short of the life expectancy his wealth and intelligence should have bought him, killed by exactly the accumulated abuse you would predict for a man who had stopped believing the abuse could reach him. His son Mark was 19. And Mark Everett has written and spoken about that morning, and the detail he keeps returning to is almost unbearable in its simplicity. He found his father's body, and in doing so he realised that it was the first time he could ever remember physically touching his father. 19 years old, and the first contact he could recall with the man who was always in the room and never reachable, the man who was like the furniture, came when that man was already a body on a bed. Think about what that means against everything we have said. A theorist who believed there was a copy of himself in every branch of reality, in countless worlds, an infinitude of Hugh Everetts, and in this branch, the only one his son could touch, the father and the boy never connected until there was nothing left to connect to. The man who multiplied himself across all possible worlds could not manage to be present in the one his children actually lived in. From inside Everett's own theory, of course, this is not the end of him. That is the part that should make you cold. By his own logic, the version of him whose heart stopped that night is just the version that, in this branch, did not make it. Somewhere in the branching, the argument says, the heart did not stop, or the ambulance came in time, or the artery held one more night, and a version of Hugh Everett continued, and from his own first-person point of view, the only one that the theory says is real to him, he never experienced that night in McLean at all. He just kept waking up. If he was right about anything, he was right about this, and if he was right about this, then his funeral, his cremation, the urn that went into the filing cabinet, all of it happened only to the version of him that the rest of us were left with. He would say he was not in it. He left instructions, as I told you at the very beginning. No burial, no grave, no scattering in a meaningful place. He wanted his ashes thrown in the trash. And his wife Nancy could not do it, not at first. She kept the urn in a filing cabinet in their home for years. This man who believed he was immortal reduced to a container of ash in a metal drawer, and eventually, because he had asked, she carried out his wish and put what was left of him out with the household garbage. The man who removed death from the equations of physics was, in this branch, in our branch, thrown away, but the instruction and the belief behind it did not stop with him. Because someone in that house had been listening, all those years, to a father who taught, in word and in the way he lived, that death was not real, that there were other worlds, that the version of you that dies is not the only version, and maybe not even the real one, and that someone was his daughter. Her name was Elizabeth. Liz. She was the older child born before Mark, and she grew up in the same cold house, with the same unreachable father and the same atmosphere of brilliant, drinking, distracted absence. And Elizabeth was not well, in a way that went beyond unhappiness, in a way that medicine in those decades was bad at helping. She suffered from severe mental illness, and over the years she was given the treatments of the time, including electroconvulsive therapy, the passing of current through the brain, and she made attempts on her own life more than once, across years. While her father grew richer and more remote, and her mother held what was left of the family together, there is one moment from this period that I have to tell you about, because it is the single most damning thing in the entire record of Hugh Everett as a human being, and because it shows you exactly what it costs the people around a man who has decided that suffering and death are not quite real. About a month before Everett's own death, in 1982, Elizabeth made a serious attempt on her life and was hospitalized, and her father, the man who believed every outcome was equally real and that no death was ever truly final, reportedly looked up from the newspaper he was reading when told how close his daughter had come to dying, and said only this: "I didn't know she was that sad. That is the whole sentence. I didn't know she was that sad. A man who had mapped the infinite branching of all possible worlds had not noticed the world directly across the breakfast table, where his own daughter was trying to leave it. The theory could hold every version of everyone. The man could not hold the one in front of him. Everett died a month later. And Elizabeth lived on for another 14 years through her 30s, carrying her illness and carrying something else, something her father had given her that no other father gives a child. She had grown up being taught, by a man she could never reach but clearly revered, that death is not what it appears to be, that there are other worlds, that the self persists across the branches, that the version of you that dies in one world goes on living in another. For most of us, that is an abstraction, a piece of physics to argue about over a drink. For a woman in profound psychological pain, raised on it by the man who invented it, it was something else. It was a door her own father had told her was real. In 1996, Elizabeth Everett died by suicide. And she left a note, and the note is the reason this story is not merely sad, but genuinely structurally horrifying. The reason it closes a loop that should never have been able to close. In her final note, Elizabeth wrote that she was going to a parallel universe, to be with her father. She asked that her remains be disposed of the way his had been, thrown out with the garbage, so that, in her words, she might end up in the correct parallel universe to meet up with Daddy. She did not see her death as an end. She saw it, exactly as her father's theory invited her to see it, as a transfer. A way of crossing from this branch, the one where her father was gone and unreachable, into another branch where the two of them could finally be together. The man who was never present in her life had given her a physics in which his absence was only local, only one branch, and she used that physics to construct a reason to die. I do not say this to indict the theory as false. Whether many worlds is true is a question about physics, and a woman's grief cannot settle it one way or the other. I say it because it is the most extreme possible demonstration of what it means for an idea to escape the laboratory. Everett built a piece of mathematics to solve the measurement problem, a technical puzzle about detectors and wave functions. And that piece of mathematics travelled, the way ideas travel, out of the journal and into the man, and out of the man and into his child. And it ended as the framework inside which a sick and grieving woman understood her own death as a journey to find her father. The personal and the physical were never separate threads. They were one thread running in both directions, from the equation into the family and back again, and at the end of it a daughter followed her father into the trash because he had taught her that the trash was a doorway. Nancy Everett, who had married Hugh in 1956, who had gone with him to Copenhagen for the meeting with Bohr that broke him, who had kept his ashes in a filing cabinet because she could not bear to throw him away, and then finally did because he had asked, did not have long after that. She died of lung cancer in 1998, 2 years after her daughter. Within 16 years, the entire family that had lived in that house in McLean was gone, except for one. The son, Mark, and Mark Everett is the reason any of this reached you at all, the reason the trash and the filing cabinet and the daughter's note are not simply lost, because Mark did something with the wreckage that almost nobody could have done. He became an artist. He formed a band called Eels, and under the name E he made records about exactly this, about a father who could not be reached, and a sister who was lost, and a mother who faded, about being the last one left in a family that had been, in his words, a kind of experiment that failed. He turned the cold house into music. And in 2007, 25 years after his father died, Mark made a documentary for the BBC called Parallel Worlds, Parallel Lives, in which he, a man with no training in physics and no real relationship with his father, set out to understand what his father had actually done, travelling to meet the physicists who now revered the man who had been furniture to him. He had grown up sharing a house with one of the most consequential minds in modern physics, and had never once discussed physics with him, and now, with everyone else dead. He went looking for his father in the equations, because the equations were the only place his father had ever fully lived. It was Mark who, around that same time, found the box. In the basement of the family home there was a box of his father's papers, the manuscripts, the letters, the working notes, the long thesis in its original uncut form, and the correspondence about its butchering. The whole record of the idea and its suppression, sitting in a basement gathering dust, and those papers, salvaged by a rock musician from a basement, became the basis for the serious historical recovery of Everett's work. The archives now held at institutions, the biography that finally told the story straight, the reconstruction of exactly how the most economical interpretation of quantum mechanics had been cut to a quarter of its length and filed in a drawer and left to wait. The proof that the establishment declined to read was preserved, in the end, not by the establishment, but by the abandoned son of the man they declined to read. So let me bring this all the way down to where it has been heading since the first sentence, since the filing cabinet, since I told you a man who believed he could not die had his ashes thrown in the trash. Here is what we actually know, stripped of comfort. The Schrodinger equation does not contain a collapse. That is not an interpretation. That is the equation. Every interpretation that hands you a single tidy world has to add something to that equation by hand to make the other outcomes disappear, and no one has ever measured that something, and no one can tell you precisely what triggers it. And the most honest reading of the mathematics, the reading that adds nothing and removes nothing, is that the other outcomes do not disappear at all. Decoherence, which has been confirmed in the laboratory, says that once those outcomes branch apart, they are sealed off from each other forever, each one a complete world with a complete copy of you in it, none of them able to reach the others. None of them more real than the rest. This is not fringe. It is held in some form by a serious fraction of the physicists who think hardest about the foundations of the field, and the version of history in which it was rightly laughed out of the room is a story told by people who found it easier to dismiss the young man than to answer him. And if it is true, then the implication that Everett took into his own body and passed to his own daughter is not a mystical add-on. It is just the equation, applied to you, without flinching. There is always a branch where you continue. Your thread of experience, the thing it feels like to be you, cannot pass through the branches where it ends, because in those branches there is no you to do the experiencing. So from the inside, from the only place you will ever stand, you do not get to an ending. You keep finding yourself in the world where you survived, down a thread that grows thinner and stranger and lonelier with every fork, while the people you love peel away into branches you cannot follow, dying in your world and living on in worlds you will never reach, exactly as Everett died in this one, and by his own arithmetic, continued in another that his son could not touch, and his daughter tried to find. That is the thing he proved, or came close enough to proving that the people who should be able to refute it cannot. Not that the universe is large, not that it is mysterious, that you are not a single life moving toward a single end. You are a branching structure, dividing constantly, and the branch you experience is selected, moment by moment, by the brute fact that you can only ever be in the branches where you still exist. The death you fear is real for everyone who watches you. It is the one event you yourself, the inside of you, the thread, will never arrive at. You will always have just barely survived. Forever, alone, eventually, in the last thin branch where the improbable run of luck that is your continued existence is still, somehow holding, he asked to be thrown in the trash. We have spent this whole time treating that as the gesture of a broken man, and maybe it was. But run it through his own theory one more time. If you genuinely believe that the version of you whose heart stops is only the local copy, that your thread continues elsewhere, then the body on the bed in McLean is not you, it is debris. It is the husk left in the branch you have already, from the inside, moved past. Of course you throw it in the trash. It is no more you than a fingernail clipping. The instruction that looks like despair is, read through the equation, the most consistent thing he ever did. He was not asking to be discarded. He was telling us, in the only language left to him, that he did not believe he was in there. His daughter believed him. She threw herself away too, looking for the doorway he had described, trying to reach the correct parallel universe to meet up with Daddy. The equation does not contain a collapse. It never did, and somewhere in the branching it describes, down a thread too improbable for any of us to ever observe, an old man who solved the deepest problem in physics at 26 and was called indescribably stupid for it, and walked away to count the dead and was thrown out with the coffee grounds, is, if he was right, still waking up. Still here, still finding himself, against all odds, alive, and he would tell you, if you could reach the branch he is in, that you are too, and that you always will be, and that this was never the comforting thought you wanted it to be.